Welcome to Spring Lib.
Once again, welcome to a new problem still dealing with diffraction. And it's always a journey where we do have a light and we have a diffraction grating. The given pieces of information is such that it's difficult to represent the entire thing, but think about these spaces. These are the open spaces that provide the diffraction, and it so happens that we do have 8,900 of these slits, and the wavelength of light that's passing through, our lambda, is given by 500 nanometers. So lambda happens to be 500 nanometers, and we can see that the slits, the specific slits, if you think about the size of these gaps, they happen to be 1.2 centimeters. Those are the sizes of the gap. Of course, the wavelength is 500, and it's going through. And now we're interested in finding the number of orders, and by orders we think about the orders on this side of the central maxima. So if you see this as the central maxima, and we're going to have an order on this side as opposed to the lower side, so we're having an order on the upper side. So we want to find those orders. N is 8,900 as given. W, which is the width of each one of these slits, is 1.2 centimeters. Lambda obviously is 500 centimeters. And we want to find the number of orders given us. And we know that d sine theta is the same as, just a little bit of distraction outside. I think it's like a plane, but it's going to be out in a minute. So d sine theta is m lambda. We want to find m, so we divide both sides by lambda. So m is d sine theta, all over lambda. We have all these pieces of data points or information. We do know that since m is d sine theta over lambda, and as you can recall, d is w over n, where w is the slit width, and n happens to be the number of slits, and d is the entire gap for the diffraction grating, the entire gap of the diffraction grating. And so we can replace d with w over n. So this is w over n sine theta, all over lambda. So w is 1.2 centimeters. Change that to meters. 1 meter is 100 centimeters, and then we have sine of theta. So this is going to be sine of 90. This is going to be sine of 90 because we're looking at the maximum order. So the maximum order. So if this angle goes all the way up until 90, so theta being 90, we're interested in the orders, but not just any orders, but the maximum order. That's what we're dealing with. So then we divide by n, which is 8,900, and lambda is 500 nanometers. Change that to meters, assuming 1 meter is 10 to the 9 nanometers, and At this point, we are comfortable finding a solution to this problem. So M is going to be 2.69. So the order is always on the lower side. So M is equivalent to order 2. So once again, we're given a problem. In this particular problem, we know that the number of opening slits is 8,900. The width of each slit is 1.2 centimeters. We want to find the maximum order. That means our angle for diffraction is 90. And the light that's diffracting is 500 nanometers. We look at the maxima, the maxima order from the central maxima that's going upwards towards the top. We know that d sine theta is m lambda. Divide both sides by lambda. We also know that the gap where all the slits are located is equivalent to a single width, W divided by N. We plug that into the formula and solve for the equation, and so we end up having 2.69. That gives us order 2. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day.